Hello, my name is Brian Lee, and this is the video report for Lab 2 in Week 6 of Principles of Physics. The mission statement of this lab is to observe the two-dimensional movement of an object that is under a constant force in one direction, in other words, projectile motion. In most cases, the force is gravity. Furthermore, the case where a drag force or air resistance is applied will also be considered. In this scenario, an object, such as a balled up sheet of paper, is thrown up into the air at an angle, resulting in an arc known as the trajectory. We will come to see that a computational model that takes in an initial position and velocity can be used to roughly predict the projectile motion of this object, although the trajectories don't line up as well as I'd expected. First of all, the main forces involved are gravitational force, often expressed as negative mg for the y component, and drag force, which has a magnitude of b times v squared in the direction opposite to the system's velocity or motion. Other relevant formulas include velocity update from Newton's second law of motion, which is v equals v naught plus f net divided by m multiplied by delta t, and position update using velocity, although which velocity to use depends on whether the net force is constant or not. For gravity only, the force is constant such that r equals r naught plus v average times delta t, v average being v initial plus v final divided by 2. The kinematic equation for position shown to the right can also come in handy as a way to combine position and velocity information into one equation. If drag is included, the net force becomes non-constant, in which case r equals r naught plus v final times delta t, as v final is a better approximation for the average velocity. Here's a screenshot of the tracker program that is used for the experiment, in which we take the paper ball as a system, and the earth and possible area of drag is considered as the surroundings. The original video has been horizontally flipped so that positive x points to the right. Immediately after being tossed, the ball's positions were recorded frame by frame, beginning with time at t equals 0.833 seconds, all the way to 1.3 seconds in 0.033 second increments. Rx or x is at negative 2.175 times 10 to the power of negative 3 meters, or negative 0.002175 meters. Ry or y is 0.3 meters. V naught x is 0.66 meters per second, and V naught y is 1.601 meters per second. Afterwards, a computational model using GlowScript to predict the motion of the ball was run, resulting in these figures. To the left are the position versus time graphs and velocity versus time graphs for the case with gravity only, whereas gravity plus drag is to the right. The 3D model of the trajectory ended up looking really similar for both, though I only included one example in the middle to show the output of the program. The underlying code is shown below, including the while loop, in which the velocity and position of the blue sphere, representing the paper ball, are updated according to the formulas mentioned previously, using the initial conditions shown before. Of note is the proportionality constant b, which is 0 for gravity only and 0.0002 for gravity plus drag. The position is updated according to which of the two cases is true, v average for gravity only and b equals 0, or v final for drag included and b equals 0.0002. And the sphere is displayed, along with arrows representing forces. The existence of the drag arrow depends on whether b is non-zero. All in all, the two datasets' trajectories line up pretty well shape-wise, but both the maximum x and y positions are not as high as in the experiment. The model's initial velocity is taken straight from the experiment, but the rest of the motion is determined purely by the forces applied. This discrepancy could be explained by a bad camera view distorting distance, human error in marking positions, bad values such as incorrect experimental velocities or a suboptimal b value, or even other forces that have influenced the trajectory to be higher in the experiment than is modeled. In conclusion, I'd say that the computational model loosely predicted the motion of the paper ball. If we were determining whether the paper ball has reached terminal velocity, I'd say no, as none of the velocity versus time graphs suggested a net force of 0. Velocity along the y-axis was still changing. The caveat is that if b were larger, it appears that the change in velocity will gradually decrease until it becomes constant, which means that the drag force is perfectly canceling out the gravity force. An experiment where an object is dropped from a sufficiently large height and where drag is considered might be better for observing terminal velocity. If the paper ball was thrown straight up, instead of some angle away from the horizontal, the drag force would be purely parallel to the y-axis, meaning the full magnitude of the drag is in the y component, rather than being distributed in both the x and y components as before. As such, The greater net force in the negative y direction results in the ball being in the air for a shorter period of time and for a smaller maximum height.